The topic of this lecture is simulation speed in logic design. This is common sense. It's always better to go faster than to go slower. Few people would argue with that. However, we often hear that other simulator characteristics are more important. Accuracy, debugging features, design turnaround time, even price. And who can argue with those? Those are important attributes. The case that I will make in this lecture is that simulation speed, or more precisely, the quantity of simulation required, has become the single most important characteristic of simulation in logic design. There are implications of this contention which are not immediately apparent. There are implications for how simulators are built, for the design methodology in which simulation is used, for HDL language features, and for the logic design style, how you express your design in the HDL which is chosen. We will cover these topics in the lecture: why increasing design complexity requires an increasing amount of simulation, efficiency considerations of hardware description languages, and efficiency considerations of HDL simulators. Let's go back to Moore's law. This is the familiar observation that says the number of transistors per integrated circuit doubles every 1.5 years. This phenomenon is the underlying driving force affecting how electronic design is done today. This law has been called one of the most significant phenomena of the computer age. It can be argued that Moore's law is somewhat dated, and the doubling time is really every 2 years or every 3 years. For the purpose of this argument, however, it doesn't really matter what the time constant is. If the transistor count goes up every so many years, that means it is exponentially increasing. If we look at some common chips, we see that the transistor count has gone up pretty much following Moore's law for quite some time. And more importantly, there is no real indication that it is going to stop anytime soon. The effects of Moore's law on end products have included increased functionality. This is fairly obvious. You put more gates on a chip and it can do more things. Other effects have included dramatic increases in performance. Performance increases have come from both increased clock rates and more internal parallelism made possible by more available logic. Finally, increased reliability, and certainly not least lower price, have resulted from the technology advances described by Moore's law. Indeed, if we look at the effects of this progression on processors over the last 2 decades, today's mainframe is tomorrow's PC. Another effect of Moore's law on end products is a shortening of product life cycles, making time to market crucial. The reason that product life cycles have decreased is that every 2 years or so, or when the technology changes, dramatic new capabilities are available due to increased integration. So if somebody brings out a product that uses technology that is only 2 years later than a previous product, the new product has a dramatically different price-performance point than the previous one. However, time to market is limited by how fast you can design a new product using the new technology. Gate counts are constantly going up. What are all those new gates being used for, and how does that affect design? Well, from the design perspective, what they're being used for is making more complex designs. At first, the tendency is to use regular structures: memories, registers, caches, and replicated functional units. Making a memory bigger doesn't really increase the complexity of the design. However, you eventually run out of benefit from regular structures, and when you have exhausted the gain obtained by replicating regular structures, you turn to irregular ones. Those are things like combinational logic, bits of state, pipelines, and control logic. This is well demonstrated by the history of RISC designs. Remember when RISC processors were simple? The MIPS R2000 had about 20,000 gates. The MIPS R4000 has about 500,000 gates. Those new gates are used to make pipelines deeper, integrate the floating point unit, and make more complicated control logic. Superscalar designs are even more complicated, with multiple functional units that have to be controlled, deep pipelines, speculative execution, branch prediction logic, and on and on. Increasing design complexity affects design methodology. People have been using design methodologies, of course, for as long as they have been designing. Those methodologies have ranged from ad hoc, seat-of-the-pants methods to very formal procedures. While you can design a 1,000 gate circuit in an ad hoc manner and get it right, you can't design a 100,000 gate circuit without a formal methodology and supporting design tools and get it right. There is just not a chance. So how can you design something with that much complexity? There have been several design methodologies which have been tried. There have been bottom-up methodologies, top-down methodologies, and inside-out methodologies. Over the past few years, the top-down methodology has become the most popular. If we look at the steps, this is a familiar procedure. Design at a high level of abstraction is the first thing that you do. You get the high-level parts of the design right. How many components you have, what the general functionality is, how the components are hooked together, what the general behavior of the system is. Then you verify the correctness. At this point, the design has become a little bit more formal, and it is in an executable representation. From that point, the design methodology takes advantage of automation. The synthesis step turns the hand-generated representation into a lower-level representation that can be used by later tools. The output of the synthesis step is the equivalent of the gate design that a manual designer would be doing. Next, place and route takes into account the physical characteristics of the process, followed by verifying the timing correctness to determine if the design does, in fact, meet the physical timing constraints. Finally comes fabrication. Levels of abstraction, which means level of detail, are associated with the top-down methodology. In general, high level means less detail, and low means more detail. There are three common levels: behavioral, register transfer, or RTL, and gate. These levels are associated with the different steps in the design process, like this. In this methodology, there is a heavy reliance on computer-aided design tools. Any step which can be automated frees the designer to spend his energy on those parts which can't. This is the hardware equivalent of using a high-level language to write a program. If you can design at a high level of abstraction, and there are translators which can transform that design into the next lower-level representation, then you don't have to worry about the lower-level details. A C programmer doesn't have to worry about the details of assembly language for analogous reasons. An interesting side effect of this is that the hardware designers are now programmers. One of the key steps in the top-down design methodology is the logic verification step, and that is the step we will be concerned with for the balance of this lecture. How do you determine that your design is correct before you proceed to the next step? Logic verification should occur as close to the actual design as possible. That way, verification is done at the same level of abstraction as the design. The designer needs to work with a single level of abstraction. This is easy to see if you relate this to programming. It is often not easy to relate a structure at a lower level to one at a higher level. This is very comparable to debugging a C program at assembly level. It is not obvious which instructions at the assembly level go with which C program statements. Likewise, it is not easy to associate gates in a netlist with a functional description of the logic. In addition, a lot of time may be spent transforming a higher level representation to a lower level one before the fix can be verified. If you are doing your design at the RTL level and your verification at the gate level, you're going to spend a lot of time doing synthesis before you can determine whether or not you got the fix right. Now, there's no real methodological requirement as to how the verification is done. There are basically two choices: formal verification and simulation. Ultimately, formal verification is the most attractive solution. That is, an analytical method which looks at the design and the specification in some way and determines if you got the design right. However, to date, this technology is not even close to being industrial strength, and as designs get more complex, the problem is not getting any more solvable. What that leaves us with is simulation. Simulation has been around as a technique for a long time and applied to many areas of system design, not exclusively electronic system design. It is a technique that works, and more importantly, it is the only one we have which we can really use. Simulation is a dynamic technique. That is, it requires the user to exercise the design in every state transition for which the system is designed before the design can be declared verified. In order to do this, a simulation model of the design is required, and simulation stimulus is required. Let's define some more terms here. We refer to the design as a model, as in simulation model. In the top-down methodology, the simulation model becomes the design itself by successive elaboration, that is, iteratively refining the model. The simulation model, and by extension the design, is specified in a hardware description language, or HDL. This is a language in which hardware behavior and structure can be naturally described. HDLs have many similarities to other simulation languages. We often refer to stimulus as test vectors, or sometimes just tests. A test vector usually includes both the input stimulus and the expected response, or output. Ultimately, tests must be derived from the specification of the system. We refer to the simulation activity generated by the stimulus as simulated cycles. This term comes from clocked logic, where the activity of the system is governed by clock cycles. Since simulation is a dynamic activity, a critical concern is providing the right stimulus for the model. You must simulate all of the behavior of the design in order to verify that it works. A common saying among hardware designers, and particularly their managers, is that if you haven't simulated it, it doesn't work. Here's where we get back to the effects of increased complexity. The amount of simulation stimulus which is required increases with design complexity. This is pretty obvious, since more complex designs usually have greater functionality, and greater functionality requires more test stimulus. However, how the amount of stimulus required is related to design complexity is not so obvious. If you add bits of state to a model, which remember is one of the uses of new gates, then in the abstract, the number of simulated cycles required increases exponentially. As you add gates to combinational logic, the number of simulated cycles required increases proportionally with the number of gates. That is because you need to have a cycle which tests each of the possible input combinations of each gate in the block of logic in order to determine that the proper output is obtained. However, the simulation time required for each cycle also increases proportionally with the number of combinational gates. This yields an amount of simulation time quadratic in the number of gates. So what we can see here is that the simulation needs are increasing superlinearly, anywhere from quadratically to exponentially, with the increased circuit complexity. In addition, the nature of the logic verification step is iterative. Simulation usually begins in a regular way as soon as the model shows signs of life. Simulation tests, or regression tests, are run continually through the design and verification process. As more functionality is added to the design, more of the test suite is run regularly to ensure that previously working features have not been broken. The model has not regressed. Consequently, not only is the total number of simulation cycles in the set of simulation tests very large, the tests get run repeatedly as the model evolves. If we look at software simulators, their speed is determined by the speed of the machine they are running on. General-purpose computers are getting faster by a factor of 2 every year. Thus, this year's software simulator can't keep up with next year's simulation needs by running it on next year's platform. It will run twice as fast, but needs to do 4 times the amount of work. Now let's turn our attention to the vehicle with which we do the simulation. There are 2 predominant hardware description languages, Verilog and VHDL. Verilog is a language which evolved from commercial use and is a de facto standard. More designs have been done in Verilog than any other HDL by a wide margin. Verilog began as a proprietary language with a simulator available from only one company, but is now an open language with simulators available from a variety of sources. Verilog will be IEEE standard 1364 in the not-too-distant future. VHDL was defined by a standards committee over the course of about a decade. It was designed to be vendor-independent, has many characteristics in common with Ada, and it is IEEE standard 1076. There were other HDLs before them. ISP, defined by Bell and Newell in 1971, is widely recognized to be the first. Other early languages were NDOT, HILO, and Helix. There are others in use today, like UDLI. HDLs themselves have properties which can affect the efficiency of simulation. If the HDL requires a great deal of work on the part of the simulator in order to implement the semantics, then a simulation may very well be slower than if the HDL had different semantic properties. If we look at the features of HDLs which affect efficiency, we find signal representation is probably the most important. Verilog has a fixed, defined set of signal representations, 4-value, 0, 1, X, and Z, and 120 value, which is a full range of signal strengths. These 2 models are built in, and whichever one is appropriate is used automatically by the simulator. VHDL, on the other hand, has a much more general model. The signal representation is not built in, but is user-definable, and in fact must be defined by the user. This has ended up with VHDL models typically settling on a few standards, a 9-value set, which is the most common, and a 46-value set. If we look at an example of 4-value data representation versus 120 value, We can see that the difference is greatest when you are dealing with vectors. That is, a collection of bits treated as a single quantity. This could be an 8-bit register or a 64-bit bus, for example. Look at a simple operation like an XOR. In the 4-value representation, the natural way to implement this is to use 2 bits per data bit, a value bit and a control bit. For vectors, the control bits can be aggregated and the data bits can be aggregated, so they can all be operated upon at once. For the 4-value representation, then, the operation can be accomplished by doing an OR on the control bits followed by an XOR on the data bits ORed with the control bits. By contrast, in the 120-value representation, each bit can have up to 120 different values. Thus, the vector must be split apart and the operation carried out in separate operations, one for each bit. This is basically an issue of scalar versus vector. If all models were scalar, that is, there were no aggregation of bits, then there really wouldn't be much difference due to representation. Since signal strength values can be represented in a byte, operations on them are always determined by table lookup. Different numbers of strengths simply result in different numbers of entries in the tables. However, models at higher levels of abstraction have aggregates of bits, or vectors. There is clearly an advantage to treating a bunch of bits at once with underlying machine instructions. If you can do all of the bits of an aggregation with a handful of instructions, then you clearly win over doing individual table lookups on every bit. Another characteristic of the HDL itself which affects the efficiency of the simulation is the issue of dynamic versus static model structure. For example, consider callbacks. In logic simulation terminology, a callback is a call to a routine when some event happens, like a signal change. So a signal changes and an arbitrary routine gets called, having been specified beforehand. You can see how this happens in the normal case. If a signal changes its value and it is the input of some gate, when that signal changes, then the new value must be propagated into the next gate. That propagation is usually done by means of a callback routine. Now, the language can allow callbacks to be specified at runtime, which means that you can essentially change the structure of the model at runtime due to data-dependent operations. Thus, a callback could be required on any arbitrary signal. If the language defines this kind of behavior, then the simulator has to allow at runtime for the possibility that any given signal could have a callback. Every time that any signal changes, it must be checked for the existence of a callback. This runtime checking can add a significant amount of extra operation to the execution of the simulation model. Another aspect of the HDL which affects simulation efficiency is scheduling. There are several delay models: transport delay and inertial delay. HDL simulators have typically used an inertial delay model because it's pretty close to what physically happens with individual gates, and it is particularly easy to implement. Here we see the difference between a transport delay and an inertial delay model. Notice that a pulse on the input in the transport delay model makes it through to the output even though the pulse is shorter than the gate delay. In fact, more than one pulse can be propagated through the gate using transport delay. The interesting thing about this is that transport delay requires dynamic event block allocation. That is, there can be an unbounded number of events associated with a single output of a gate that are scheduled at one time. And in fact, you can't determine the maximum number at compile time. Using the inertial delay model, however, causes the pulse to be swallowed, so it does not appear on the gate output. With inertial delay, there is only one event scheduled. When it is scheduled, may be subject to differing interpretations of the inertial model, but there will be only one event which allows the simulator to simply allocate an event block statically and leave it around for all time. We can look at a subtle difference between Verilog and VHDL in this regard. Both of them use inertial delay, but Verilog has a second inertial delay model. Verilog's original delay model is just like the VHDL version. If an input pulse changes before the gate delay, then the output event would be unscheduled from the future event list and then rescheduled for the new time. In Verilog's second delay model, called the XL model, the event is simply left on the list, and the new value is propagated at the old time. In the vast majority of cases, this results in the same model behavior at a considerable saving of time. In summary, the semantic restrictions imposed by the HDL, or not imposed, can make a significant difference in simulation speed. Now let's talk about some of Verilog's characteristics which contribute to efficient simulation. Verilog has natural data structures built in: scalars, vectors, memories, gate types, and resolution functions. The great advantage of having these features built in is that they can be implemented efficiently. This is a rich enough feature set so that most designs can be represented using them. Verilog also has reasonable model constraints. The resolution functions which are built in are adequate. There are 8 of them, they are not exotic, and they are generally sufficient. While there may be cases where the user would like to define his own, as he can do in VHDL, that is pretty rare. An example of reasonable model constraints is the use of events on signals. Compare the VHDL description of the rising edge of a clock event with that of Verilog. The if statement, which has 3 different components, is what is required to determine that a rising edge occurred. An event happened on the signal clock. The new value is 1 and the last value is 0. That is a very complete description of the event. But look at the Verilog representation, at pause edge of clock. It is up to the simulator to implement this in the most efficient manner it can. Another characteristic which Verilog has, which is both good and bad, is that it is not over-constrained. Some behavior is undefined. In fact, a lot of behavior is undefined, and race conditions are possible. Here we see an example of a race. A race condition is defined as a case where one event is sampling a signal value at the same simulation time that another event is changing it, and the order of event execution is not defined. Thus, in one simulation the race could go one way, and in another it could go the other way. Hardware, in fact, is full of these kinds of considerations. It is quite easy to design hardware with races in it. It's obviously not a good thing to do. Likewise, it is not a good thing to do it in a Verilog description of the model. However, because of this flexibility, or lack of rigid definition, the implementation of the simulator is free to execute concurrent events in whichever order is most efficient. For example, the simulator may combine 2 events into one if the ordering constraints are loose enough, saving a measurable amount of overhead. If we look at this example of a gated clock, which, by the way, is a pretty bad design practice, we see that propagation order can affect the model behavior. Assume that A changes at time t. Then statement 1 will be evaluated. Since B changes, its new value must be propagated to statements 2 and 3 because their right-hand side expressions use it. Once C changes, statement 3 must be evaluated again. If statement 3 were evaluated before the propagation of C from statement 2, then statement 3 would have to be evaluated twice. If statement 2 were evaluated before statement 3, then statement 3 would only need to be evaluated once. Notice that one way there are 2 changes on D, and the other way there is no change, triggering the counter in one case and not in the other. VHDL defines the ordering of events in such a way that this model would be executed the same way every time in all different simulators. It would be done in such a way that there would be a pulse on D. In Verilog, however, the propagation order is not rigidly defined by the language, and if you write such a model, the 2 assignments could execute in either order. Because of this, the Verilog simulator can reduce the number of events that can happen and can generally execute faster. It is up to the model designer to avoid doing things like this if they will affect the behavior of the system. Verilog has efficient data representation. The 4-value representation is usually sufficient to handle most RTL models. Because of that, it offers the simulator the opportunity to optimize 4-value operations and execute much faster than if you have to use more than 2 bits per bit for internal signal representation. Another feature of Verilog which contributes to efficient execution is early binding. Verilog does not have runtime parameters like VHDL, but it has compile time parameters. These are essentially constants that are used for things like binding sizes at compile time, not runtime. Look at this example of a shifter, a module which can do an arbitrary length shift of 1 bit position. The argument val is a variable length vector whose length is determined at runtime by the attribute val prime length. If you do this in VHDL, you only need one description for any width of shifter. The width is determined at simulation time. So if your model has a 2-bit shifter and a 64-bit shifter, there is only one piece of code which represents them both. In Verilog, though, while you still have only one piece of source code, the width is determined by a compile time parameter. Thus, the 2-bit shifter would result in one module at simulation time, and the 64-bit shifter would result in a different one. Each of these would be faster than a more general module which could handle both widths. Now let's look at some examples of efficient Verilog coding techniques. The most important thing you can do to write efficient models is to use high-level constructs. Use behavioral rather than gate-level code. This is somewhat implementation dependent. You can certainly write a Verilog simulator in which gate-level models run faster than the equivalent behavioral models, and in fact, the first Verilog simulator was written this way. But in modern implementations of Verilog, it is clearly better to write at a higher level of abstraction using aggregation. We can see why with this example of an 8-bit AND operation. In the aggregated 4-value case, 5 operations are required, while in the gate-level case, 8 table lookups need to be done. For this reason, it is important to write Verilog code which avoids use of 120-value vectors whenever possible. If you can use 4-value representation on vectors, your simulation model will run much faster on vector operations than if it has to be broken out bit by bit to implement different strength values. Another way of using different levels of abstraction involves the difference between procedural and declarative coding. With Verilog, there are declarative statements and procedural statements. Whereas the declarative ones get reevaluated every time any value used in the right-hand side expression changes, procedural statements are evaluated only when the procedural block is active. Procedural statements are executed sequentially, subject to timing controls. In this example, a set of assignments are done at the time that signal X changes. Since they are declarative statements, the entire right-hand side of each assignment is evaluated at the time X changes. In the corresponding procedural code, this block is conditioned on the changing value of X, whereas only the necessary computations are done as the different assignments are made. You can see that the expression X and Z is executed only once in the procedural block, but twice in the declarative code. This is a relatively significant technique, and it can make a big difference in the execution time of your models. This leads into the efficient coding of state machines. Synthesizable code is full of state machines, especially in synchronous designs. Synthesizers deal with state machines in stylized ways, and there are more and less efficient ways of doing them. Here we see a simple way of coding a state machine. The continuous assignment evaluates the new state function every time the input changes, and the new state value is sampled on the rising clock edge. The new state function may be evaluated more than once in a cycle. We can fix that by writing the state machine so that the new state function gets executed on the rising edge of the clock. While this is better for the case of input changing more than once in the clock cycle, it executes every cycle, which may be more often than necessary if input does not change that frequently. This version accomplishes what we want. On those cycles where input changes, new state is evaluated once at the rising edge, allowing any glitches on input to settle out, and the state variable is updated. Now let's look at the difference between blocking and non-blocking assignments in procedural code. A blocking assignment is one in which the right-hand side expression is evaluated and assigned immediately to the left-hand side. A non-blocking assignment is an assignment in which the right-hand side is evaluated and saved in a temporary location, and the assignment is done to the left-hand side at the end of this time step, after all right-hand side evaluations have been done. The difference between the two is that if you replace the blocking assigns with non-blocking assigns, there will be 2 events instead of 1. The first event is the one in which all the right-hand sides are evaluated, and the second event is the one in which all the assignments are made. In some cases, this is very convenient and is a compact notation. Our state machine could be written using a non-blocking assign like this. However, non-blocking assigns can affect the simulation speed. If you can write a model which uses blocking assigns instead of non-blocking assigns, and you don't have to add another event, it will run faster. In this example, using non-blocking assigns will run almost twice as slow as using blocking assigns. We can talk about inefficient coding techniques as well. There is a class of construct called a bidirectional pass transistor, or the tran and rtran primitives. These are bidirectional primitives in which the primitive evaluation needs to be done on both ports. Both of them are in-out ports. And a resolution function needs to be applied to both of them to produce a value whenever either port changes. This can be expensive in the simulation. The example we have here is a model of a static RAM cell with a bidirectional transistor. A gate-level version of this simply has one primitive for each gate in the schematic. Models which use bidirect primitives are usually much less efficient than those that don't. In many cases, we can simply rewrite the low-level model at a higher level. This version simulates much faster than the bidirectional version. The interesting thing is that in many cases, the bidirect is being used simply as a notational convenience, and the logic of the model allows it to be replaced by a unidirectional primitive, which will simulate much faster. For example, a bidirect is often used to model a resistor, which can be modeled with a unidirectional primitive. It is often the case in an HDL that if you use a more general construct than necessary, the simulation will be slower than it could be. Another important category of avoidable overhead is specifying unimportant delays. For example, suppose you have a library of macro cells from your silicon vendor, and that library includes detailed timing information. If you are doing a synchronous design in which you know you will be doing logic synthesis and static timing analysis, then the detailed timing information may not be of any interest at all to you. However, it is of great interest to the simulator and will cause it to do a lot of work, scheduling events at different times due to the timing specifications. So in general, if you are not concerned with detailed timing, you shouldn't include the delays in the model. Here's a more subtle coding technique which can have large performance effects. Look at this example where there is more than one function on the right-hand side of an assignment in declarative code. If you write the model this way, you will have each of the functions f1 and f2 evaluated every time any of the arguments on the right-hand side changes. Thus, if x changes, both f1 and f2 will be reevaluated rather than just f1. This is required semantically for obscure reasons. We can see that this can be a fairly significant amount of overhead if the functions are at all complicated. To avoid this reevaluation, you must use intermediate assignments like so. Writing the assignment this way in essence tells the Verilog compiler that there are no undeclared dependencies between f1 and f2. Another example which is similar in spirit to this is the cascaded ? This is often used for multiplexing different expression values onto an output signal. Whenever anything in the entire right-hand side changes, all the expressions in the right-hand side get reevaluated. If you rewrote it in such a way that the multiplexed values were temporaries, as we did in the function example, then only the appropriate right-hand side expression would be reevaluated, and the whole thing would go much faster. Now let's talk about how simulators are built. If we look at this chart, we can make up a taxonomy of simulators. They can be categorized as dynamic or static, and interpreted or compiled. We've been talking about dynamic simulators. We've done that implicitly by the semantics of the language we've talked about. We should note that there is a significant class of simulators which are static. That is, they don't use dynamic scheduling, and they don't have event routines. They simply order all of the evaluation elements, typically gates, in rank order from input to output on clock boundaries, and on each clock, all gates are evaluated in turn. This leads to very fast gate evaluation. However, it has the obvious disadvantage that all the gates in the entire model get evaluated every clock cycle. They also have the disadvantage that these have been limited to synchronous designs, and sometimes level-sensitive designs. These simulators also don't deal with asynchronous feedback loops, which is a problem, though it is of diminishing importance. In the case of static simulators, there are really no examples of interpreted simulators. They are all compiled. In fact, this class of simulators has often been called levelized compiled code simulators, causing some confusion with dynamic compiled simulators. Dynamic simulators are a much larger class and the more standard type of simulator. This is due to the semantics of the HDLs, which can represent more real circuits. The semantics of all the popular HDLs require dynamic scheduling. Within this class of simulator, there are interpreted simulators and compiled simulators. By these terms, we mean exactly the same thing as when we talk about an interpreter or a compiler for a programming language like Fortran. In essence, we have interpreters for HDLs and compilers for HDLs. The interesting characteristic of HDLs is that at low levels of abstraction, interpreters can be pretty fast. There really is not a whole lot of difference between an interpreter and a compiler on gate-level models. It is only when you get to RTL and behavioral levels that a compiler exhibits the dramatic performance improvement that you would expect. In general, the difference at these levels between a compiler and interpreter is about the same as what it is for any other programming language, often more than an order of magnitude. The reason for that is pretty simple. A hardware description language at behavioral level looks a lot like a programming language. Traditional compiler techniques are more effective on that kind of model description than gate-level techniques are. and certainly more effective than interpretive techniques. As a result, as the pressure on design methodology has moved the focus of design onto higher levels of abstraction, compiled simulators are much more important than interpreted simulators. In a relatively short period of time, we will probably see the last of modern HDL interpreters. They are simply no longer competitive. There is always an issue of compile time. Interpreters are very quick to get to the start of simulation. This is the case with virtually all interpreters, and that is their big advantage. Compilers, on the other hand, take a fairly significant amount of time to turn the HDL source into an executable program. The good news is that while compile time is a relatively slow, or at least computationally intensive activity, as computers get faster, compile time gets to be less of an issue. Indeed, the compile time is more or less linear with the size of the input, and, as we have seen, simulation time is at best quadratic. The underlying hardware that is doing the compilation is, in fact, getting faster by the usual doubling of speed every year. The other reason that compile time is not an issue is that incremental compilation is available with a compiler. It is typically not available in an interpreter. In a compiler, you are free to compile only the part of the model which is changed. The semantics of the language can make this a more or less complicated activity. It is the case with Verilog that the entire model source must be inspected whenever any change is made to any component of a model to see if, by chance, it has affected some other part of the model. Fortunately, the source inspection is confined to the first pass of the compiler, so most of the work can be avoided for all those modules which have not changed. Thus, incremental compilation really does make compile time a minor issue. The other advantage that interpreters have is that typically they offer better debugging capabilities than compilers do. However, compilers have been offering good interactive debugging capabilities for a long time, and HDL compilers are no exception. You can do most of the things interactively that you need to do. You can monitor signals, stop at breakpoints, change register values, invoke functions, pretty much the usual collection of activities. It is also the case that much of the simulation activity in the design process is spent in regression testing, where debugging is often done in an offline fashion. You simply dump all the signals out somewhere around the time of the error and analyze them using a post-processing tool of some sort. This is a relatively effective way of debugging a model. So what we conclude is that compiled simulators have adequate debugging capabilities, they have acceptable compile time, and their simulation time is so far superior to interpreters that there is really no longer any point in dealing with interpreters for industrial strength simulation. Now let's talk about a particular simulator, VCS, the Verilog Compiled Simulator from Chronologic Simulation. VCS is event-oriented, it has a scheduler, it has event routines. You can't do Verilog without those features. For performance, this is a drawback. If you could avoid the scheduler, you could save a significant portion of the simulation time. VCS is a compiler. It produces compiled code. It is, in fact, the fastest HDL simulator around today. VCS gets its speed from its underlying implementation strategy. It uses compiled code, it does event optimization, it does code optimization, and it minimizes model size. An event-driven simulator must do three things: logic evaluations, signal propagation, and event scheduling. Of these three, logic evaluation tends to be most time-consuming, though all three are significant. Logic evaluation can be done fastest using compiled code. Event propagation can be done as efficiently using compiled code as any other way, and event scheduling can be implemented efficiently using most simulation strategies. Consequently, compiling the logic operations of the model yields the fastest simulation. The next most important performance-related strategy is event optimization. Here is an example of reducing events by combining them. In many simulators, this would be done with two events, one to evaluate x1 and the second to evaluate x2 as a result of the propagation of x1. In VCS, the second event will be inlined into the propagation routine of x1, so there is only one event executed. Typically, a lot of time during simulation is spent in propagation routines, scheduling evaluation routines which are dependent on the signal being propagated. Propagation routines can either be scheduled or called directly, and still obey Verilog semantics. Likewise, evaluation routines which depend on propagated signals can often be called directly. By recognizing when it is best to call both propagate routines and evaluation routines directly, VCS can reduce the number of events executed, thus reducing the overhead of the scheduler. VCS also does general code optimizations. It does common subexpression elimination just like any other compiler would, and it does temporary variable analysis. It puts temporary variables on a stack rather than putting them in the permanent storage for the module instance. The initial implementation of VCS produced C code as its output rather than machine code as a traditional compiler would. Low-level C code is produced by VCS, and the host machine's C compiler is allowed to optimize it. That has some pretty good consequences for the quality of the code generated, because there have been literally hundreds of man-years of effort put into generating good C code for any given hardware manufacturer's C compiler. There is no hope that you would ever put that kind of effort into an HDL compiler's code generator. On the other hand, there are some advantages to omitting native code. For instance, if you omit native code, you are free to use calling conventions which are not the standard C conventions. This may allow a lighter weight event routine calling convention, which can save quite a bit of time. If you can save a few instructions on every event routine call, that can definitely be a measurable amount of time saved. This may very well make up for the poorer instruction scheduling which the HDL compiler might do compared to the C compiler. Another significant factor is that the HDL compiler knows about relationships between variables that the C compiler must infer from the C source. This knowledge can result in better register allocation or code optimization, which can be significant. The end result of all this is that there is not a really compelling difference in runtime performance between a C implementation and a native code implementation of an HDL compiler. This is true with both VHDL and Verilog. In theory, if you put enough effort into it, native code would be somewhat better. But it does require a lot of effort to get comparable instruction scheduling, which is an important aspect of runtime performance. The end result is that the most compelling difference between C code generation and machine code generation is the compile time advantage machine code has. Finally, VCS optimizes memory usage. VCS does this with reentrant code for each module type. There is one piece of code for each unique module type and different activation records for each instance. This has a dramatic effect on memory consumption compared with other simulators. This not only allows simulation models to run on smaller machines, but has a positive effect on speed as well. So how does all this stuff work out in real life? Let's look at some benchmark results. We can show comparisons between VCS and the standard interpreted Verilog simulator. In the following benchmarks, we can see that the gate-level models in the VCS compiler run about the same speed as in the standard Verilog interpreter. The RTL models run considerably faster, about an order of magnitude faster than an interpreter, and behavioral models run even faster. As the level of abstraction increases, the relative speed difference increases as well. Here is an interesting set of numbers which shows simulation times on a variety of different simulators running the same model in both VHDL and Verilog. Here you see the differences between compiled and interpreted simulators, and you can also see the differences between native code and generated C, as well as a comparison between VHDL and Verilog simulators. We can see that the combination of Verilog and compiled C is far faster than any of the other combinations, but we don't have a native code Verilog compiler in this group. One of the measures of logic simulator performance has been events per second. This is a meaningful term for gate-level simulators, where all simulators would execute a similar number of events for a given model. For HDL simulators, this is not a meaningful term. There can be different numbers of events depending on the implementation of the simulator. A more interesting number is model-related, and that is simulated cycles per second. Of course, this is highly model-dependent. You can have models which have a lot of activity for every simulated cycle, and you can have models with very little activity, and they will have wildly different numbers for this metric on the same simulator. An even more interesting metric, which we won't mention further, is simulated cycles per dollar. That may be the one that is the most important to you. We can ask, where are we going from here? We have compiled Verilog as the fastest HDL simulation capability today. How are we going to get faster in the future? As we have seen, we certainly have to improve our performance because the requirements are going to keep going up. Parallel simulation is one area that people are looking at now, and it does hold some promise. Logic simulation is perhaps a little easier problem than the general-purpose parallel simulation problem. Speculative execution has never worked in the research projects in which it has been tried, while there have been at least a few modest successes with event list parallelization. Maybe a more interesting direction for the future is in higher-level simulation. What's called cycle-accurate simulation is one approach to this, and that is an attempt to reduce the number of events to one event per cycle. This is, in effect, a combination of static simulation with dynamic simulation. While you can't do full Verilog or VHDL semantics this way, you can do enough to be interesting for many classes of designs. Higher-level synthesis complements this. If you can design in a simpler manner, and the HDL description of your model obeys these constraints, then your simulation can go much faster. Another technique, which is not simulator-related, is design reuse. This is where a known, verified chunk of logic is dropped into a model. Since that logic has already been verified, only the interface to the rest of the system must be verified. While it is too early to predict with any assurance where the next big improvements in simulation speed will come from, it is likely that some aspects of all these possibilities will be found in future high-performance simulators. What we have covered in this lecture is the crucial role of simulation speed in logic design. We have discussed the necessity of simulating at the appropriate level of abstraction, the increasing quantity of simulation required, some of the efficiency effects of the hardware description language itself, and finally the characteristics of a speed-oriented Verilog simulator. The message of this lecture has been that speed counts. Increasing complexity is unrelenting, and as long as we use simulation, speed will be of fundamental importance. Thank you.